This awkward-looking ugly duckling was considered an easy target and a disgrace to designers, yet it went on to help win the Second World War, becoming a legend for all time. We are used to seeing the Sherman as a symbol of Allied triumph, but few know the crazy compromises required just to bring this machine into existence. Why did they start designing the tank for Lend-Lease even before the blueprints were approved? Why did they literally force an aircraft engine into it? And how did this technological Frankenstein manage to travel thousands of kilometers without repairs, defying all laws of logic? Today, we will brush the dust off the legend and look into the closed reports of those years. Watch this video to the end. You will discover the behind-the-scenes story of the M4's creation, which will make you look at the history of the Allies' main tank in a completely different way. Let's begin. May 1940, France. German armored columns passed through the Ardennes forest in 3 days, a forest that French generals considered impassable for military vehicles. They miscalculated, and the price of this mistake was catastrophic. Within 6 weeks, France fell. The British Expeditionary Force barely escaped through Dunkirk, leaving hundreds of vehicles on the beaches. The map of Europe was changing so rapidly that staff officers could not redraw the front lines fast enough. Washington watched this with growing concern. The United States Army in 1940 possessed about 300 tanks. 300. For comparison, by that point, the German armored divisions numbered thousands of vehicles that had already fought through Poland and France. This was not a gap, it was an abyss. But it was not just about the numbers, it was about the very concept of tank employment. American military theorists viewed armor as infantry support, slow, cautious, and secondary. The Germans saw it differently. For them, the tank was the primary instrument of breakthrough, an independent strike force. This difference in thinking determined the outcome of the 1940 campaign. In July of that year, the United States Army Ordnance Committee met with a single agenda: what to do. The request was direct. A medium tank was needed, featuring a fully rotating turret, a gun capable of engaging both armor and infantry, sufficient range for real operations, and, most importantly, a design that American industry could manufacture by the thousands. This last condition was fundamental. In 1940, the United States did not have a single factory specialized in producing tanks on an industrial scale. There were no established supply chains, no trained workers, and not even standard specifications for mass-producing armored vehicles. Everything had to be created from scratch, simultaneously with the tank itself. Engineers at the Aberdeen Proving Ground set to work. The project received the designation T6, which would eventually become the M4 Sherman. But that was still a long way off because first, an inconvenient problem had to be solved. A rotating turret with a proper gun sounds simple, but in practice it meant redesigning the entire hull, recalculating the center of gravity, and completely rebuilding the layout of the fighting compartment. This was a task of many months, and they did not have months. Europe was already on fire. The British were losing equipment faster than they could replace it. They needed tanks, not blueprints, promises, or concepts. Tanks, now. And this is where American military planners made a decision that might seem strange at first glance. They put into production a tank that they themselves considered imperfect. While engineers were still refining the T6 and its rotating turret, the Army began mass production of an interim vehicle, the one that was ready in time, whose main gun was mounted not in a turret, but in the side of the hull, in a sponson. This vehicle was the M3, which the British named the Lee and the Grant. And it was the M3, with all its compromises and limitations, that bought the Sherman project the necessary time. The M3 did not appear because anyone particularly wanted it. It appeared because the Allies had no other choice. Understanding this is crucial, as the entire logic behind the creation of the Sherman lies in this forced decision. Let us take a step back. By 1940, the British Army desperately needed medium tanks armed with a 75mm gun. Not a light gun, not a purely anti-infantry weapon, but a 75mm gun capable of engaging both armored targets and fortified positions. The Americans were ready to help. The Lend-Lease Act, a program for supplying equipment and materials to the Allies, was signed in March 1941. The only problem was that a suitable tank did not yet exist. The T6, the future Sherman, was in development, but mass production was still months of hard work away, while deliveries were needed immediately. So, engineers took the chassis already in production from the M2A1 light tank, widened the hull, thickened the armor, and installed a 75mm gun. But where to place that gun became a real headache. A rotating turret for such a weapon required a different hull geometry, a different weight distribution, and different layout solutions. This was work that could not be done properly in a short time frame. Consequently, they made a decision that seems almost comical today. The gun was mounted in a sponson, a projection on the right side of the hull, with a limited traverse arc. On top, in a small turret, they placed a 37mm gun, which was the primary weapon on paper, but auxiliary in practice. The result was a vehicle with two guns and severe limitations on the use of the main one. The 75mm gun in the sponson could only traverse a few degrees in either direction. To fire at a target to the side or rear, the tank had to turn its entire hull. In real combat conditions, this created obvious difficulties. The crew consisted of 7 men, more than most contemporaries. The vehicle's height exceeded 2 meters and 70 centimeters, making it a prominent target. The British received the M3 in two versions, the Lee, featuring the American cupola and an additional machine gun turret on the roof, and the Grant, with a modified turret without the top cupola, built to British specifications. The difference lay in the details of the turret layout, but the essence remained the same. It was a transitional tank, and everyone understood this. Nevertheless, the M3 played the role expected of it. It arrived in the right place at the right time. The first M3s arrived in North Africa in early 1942. British crews initially viewed the American vehicle with suspicion. It was tall, had an unusual layout, and felt cramped inside with 7 men. However, when it turned out that the M3's 75mm gun could penetrate the armor of German medium tanks at distances where the Germans could not yet return effective fire, the attitude changed. The M3 was not a perfect tank, it was an adequate tank. That was exactly what was required of it. And while it was fighting in the African desert, something important was happening in factories across the United States. M3 production helped establish supply chains, train workers, and identify bottlenecks in logistics. In essence, American industry underwent a trial run on a transitional machine that no one had originally considered the final answer. This was precisely what the engineers of the T6 project needed. While the assembly lines were turning out M3s, the designers quietly finished what they had not had time for earlier: a fully rotating turret, a correct layout, and a normal crew of 5 instead of 7. A vehicle that did not need to turn its hull to fire at a target to its right. By September 1941, the prototype T6 was ready for testing. It was inspected, fired upon, and driven around the proving ground. The commission approved it, and the vehicle was accepted into service under the designation M4. It was named later in honor of United States Civil War General William Tecumseh Sherman, following the British tradition of naming American tanks after American generals. The tank was ready. Now it had to be produced in quantities that would change the course of events. In February 1942, the first production M4 rolled off the assembly line at the Lima Locomotive Works in Ohio. Lima Locomotive Works, the name speaks for itself. This enterprise built steam locomotives, heavy, complex freight engines requiring precise metalworking and the assembly of large steel structures. Prior to February 1942, they had not produced a single tank, none at all. And yet, this factory was the first. This was not an accident, it was a deliberate choice. American military planners understood that building tank production facilities from scratch would mean losing a year or more. However, by taking enterprises that already knew how to work with large steel structures, precision machining, and multi-stage assembly, and redirecting them to a new product, the setup time could be reduced dramatically. The logic was simple. A locomotive and a tank are different machines, but metal is cut the same way. The Lima plant received the documentation, equipment, and assignment. Engineers studied the drawings, workers were retrained, and supply chains were reorganized. In February 1942, the first production M4 drove out of the gates of a facility that just months earlier had produced nothing but locomotives. But one factory was not an industry, it was only the beginning. Other enterprises began to join production in parallel. The Pullman Standard Car Manufacturing Company, the country's largest passenger rail car manufacturer, began using its workshops in 1942 to produce armored hulls and assemblies for the M4. The Federal Welded Company specialized in welded structures, mastering the production of welded hulls for later versions of the Sherman, which replaced the early cast hulls. The Chrysler Automobile Corporation set up production at the Detroit Tank Arsenal, a specialized facility built in Warren, Michigan. This plant was originally designed like an automobile factory and was repurposed in record time, taking about a year from breaking ground to producing the first tank. The Fisher Body division of General Motors, which previously manufactured car bodies, mastered the production of turrets and hulls. The plant in Grand Blanc, Michigan was built specifically for wartime needs during the conflict. It became one of the country's largest tank plants, an enormous production complex erected from scratch in a matter of months. Think about this for a moment. A country that in 1940 did not have a single specialized tank factory built several such enterprises within 2 years, some of them during active hostilities. At the same time, existing plants transitioned to military production without stopping their operations. The initial plan called for a combined output of about 1,000 tanks per month across all enterprises. This figure seemed ambitious, yet it was surpassed. As new factories reached their design capacity and production processes were refined, monthly output began to grow. The logic of the assembly line worked at full strength. The more machines produced, the better the process was mastered, and the faster the next batch went through. Here, it is important to speak about the design of the Sherman itself, how it was structured from a manufacturing perspective. The lower hull was welded, and the suspension bogies were bolted to it, not welded. This solution had a dual purpose. First, a bolted connection is simpler to manufacture, as it does not require complex fixtures for welding in hard-to-reach places. Second, and this would prove extremely important in practice, a damaged suspension bogie could be replaced in the field without heavy lifting equipment and without returning the vehicle to a factory. The lower front hull on early versions consisted of 3 armored steel plates bolted together. Later, the bolted connection of the front plates was abandoned in favor of welding, which simplified production and improved the protection of the joints. The upper hull of the first production Shermans was cast, with the entire component poured as a single piece in special molds. The cast hull had rounded shapes, which provided a certain ballistic advantage, as shells were more likely to glance off rounded surfaces than flat ones. However, casting was slow and required specialized equipment. On later production runs, the upper hull was welded from flat armor plates positioned at sloped angles. A sloped plate of the same thickness provides better protection than a vertical one, as the projectile travels a longer distance through the metal and is more likely to deflect or lose energy. In total, from July 942 to January 944, 6,748 tanks of the basic M4 modification were produced. That was just the basic version. Concurrently, production of the M4A1, M4A2, and M4A3 modifications was underway, utilizing different engines and layout solutions. The total production of all Sherman modifications over the years of manufacture amounted to 49,234 vehicles. 49,000. For comparison, Germany produced about 8,400 Panther tanks, a vehicle often considered one of the best medium tanks of that period. Almost 6 times as many Shermans were built. This is not just a production statistic, it is a strategy. American military planners relied not on creating a perfect tank in small numbers, but on producing a sufficiently good tank in overwhelming quantities. This philosophy remains a subject of debate among historians to this day, but it yielded a very definite result. And this result underwent its first test in a place where one might least expect technical breakthroughs: the desert. A tank is not just armor and a gun. A tank is how it moves, how it takes a hit, and how it behaves on different soils. In this sense, the Sherman suspension and running gear represent one of the most indicative aspects of its design. Let us start with what is visible from the outside. The Sherman utilized a suspension system designated in technical documentation as VVSS, vertical volute spring suspension. To put it simply, there were 3 bogies on each side of the hull. Each bogie contained 2 road wheels on a common axle. Between the bogie and the hull was a vertical spring that absorbed shocks from uneven ground. American designers had used this scheme on their tanks since 1937. By the time the Sherman appeared, it was well studied, proven in production, and understood by mechanics. This was an important point. A familiar design meant predictable behavior in operation and quick repairs by the crew. The drive sprocket, the one that transmits power from the engine to the track, was at the front, while the idler wheel, which adjusts track tension, was at the rear. The tension was adjustable, allowing the crew to compensate for track wear without replacing the track entirely. The track itself consisted of 78 links, or blocks, connected by pins. The width of the standard track was about 16.5 inches, approximately 42 centimeters. For a vehicle weighing about 30 tons, this provided acceptable ground pressure on firm surfaces. However, on soft ground, such as mud, snow, or sand, the narrow track sank deeper than desired. This limitation was known from the beginning, and it was eventually addressed, but more on that later. Now, regarding how the bogies were attached to the hull, each of the 6 bogies, 3 on each side, was bolted to the lower hull, not welded. To someone unfamiliar with military hardware, this might sound like an insignificant detail. In practice, this design choice was of immense value. Imagine a tank is hit and a shell fragment damages a suspension bogie, rendering the vehicle immobile. In a factory environment, this is solved easily. A crane removes the damaged unit and installs a new one. But tanks do not break down in factories. They break down in the field, sometimes under fire, and sometimes hundreds of kilometers from the nearest repair base. The bolted attachment meant that a crew with a set of tools could remove a damaged bogie and install a spare without heavy lifting equipment, right in the field, in a few hours instead of several days. This was why the Sherman maintained such high operational readiness in real-world conditions. Let us move on to the hull. The lower hull was welded. Large armored steel plates were joined by weld seams, providing a monolithic structure without bolted joints that could become weak points when struck by a shell. The lower front section on early vehicles consisted of 3 separate armor plates bolted together. Subsequently, this design was abandoned in favor of a single-piece welded front section, which was simpler to produce and more reliable in combat. The upper hull of the first production Shermans was cast. The entire piece was poured in special molds. The cast hull featured rounded shapes, offering a certain ballistic advantage as shells were more likely to deflect off rounded surfaces than flat ones. However, casting was slow and required specialized equipment. On later production runs, the upper hull was made welded, using flat armor plates arranged at sloped angles. A sloped plate of the same thickness provides better protection than a vertical one, as the projectile travels a longer path through the metal and is more likely to deflect or lose energy. Armor thickness varied depending on the area. The front hull plates had a thickness of 76 millimeters. This was the main protected zone, the part facing the enemy in a head-on engagement. The turret and upper hull plates were 51 millimeters thick, while the sides and rear were about 38 millimeters. The floor and roof were significantly thinner, as threats from those directions were considered minimal in 1942. These figures must be understood in context. In 1942, 76 millimeters of frontal armor provided sufficient protection against most anti-tank guns used by the enemy at the time. The situation would change rapidly as the adversary fielded more powerful artillery, but at the time of the Sherman's introduction, its armor met the requirements. The hull featured 3 standard hatches for the crew, 2 in the front for the driver and co-driver, and 1 in the turret for the commander and loader. In addition, there was an escape hatch in the floor, beneath the driver's seat. If the crew could not exit through the upper hatches, under fire, with a jammed turret, or during a fire, there remained an exit downward, through the floor. This solution seems obvious, but by no means did all tanks of that era feature it. The Sherman gave its crew a chance to get out, and this was also an intentional part of the design. When discussing a tank, people usually talk about the armor, the gun, and the engine. They less frequently discuss the people inside. Yet, a 5-man crew is not just a group of operators. They are a system whose coordination determines everything else. The way the Sherman's designers arranged these 5 men says a lot about the philosophy of the entire vehicle. Let us start at the front. The driver sat on the left side of the driving compartment at the front of the hull. To his right sat the co-driver. Between them ran the transmission drive shaft along the floor of the compartment. The space was limited but well planned. The driver had at his disposal 2 steering levers, accelerator and brake pedals, and a gear shift lever for the manual transmission, which featured 5 forward gears and 1 reverse. Steering was achieved through a differential mechanism that braked one track relative to the other during a turn. This allowed the tank to turn smoothly, without jerking, which was important when driving over rough terrain. In front of the driver was a periscope offering an external view. On early vehicles, there was an additional vision slot in the front plate protected by bulletproof glass and an armored cover. However, practice showed that the glass would cloud and crack from near misses by bullets and shrapnel, severely reducing visibility exactly when it was needed most. On later production runs, these slots were abandoned, leaving only the periscopes. To the right of the driver sat the co-driver. In peacetime, this role might sound unusual, a second driver who almost never drives. However, in combat conditions, the co-driver performed an important function. He operated the bow Browning 7.62mm machine gun mounted in a ball joint in the front hull plate. The ball mount allowed the machine gun to be traversed within a small horizontal and vertical range without changing the position of the tank. The field of fire was limited, about 20 degrees to either side of the vehicle's centerline, but this was sufficient for engaging infantry directly ahead. Additionally, the co-driver could take over steering if the driver was incapacitated. This duplication of functions was characteristic of the American approach to design, providing a backup option in the event of losing a crew member. Let us move to the turret. The Sherman's turret rotated together with the floor of the fighting compartment. This is a crucial detail that is easily underappreciated. In tanks where the turret rotated independently of the floor, the turret crew faced an awkward situation during rotation. They sat stationary while the space around them shifted. Their feet could strike the hull sides, and the loader could lose orientation relative to the ammunition stowage. In the stress of battle, this created real problems. The rotating floor resolved this. The entire turret crew rotated along with the gun. The loader always knew where the shells were, the gunner did not get tangled in pedals, and the commander maintained his orientation. To the left of the gun sat the loader. His job was physically the most demanding. A fixed round for the 75mm gun weighed about 8 kilograms. In intense combat, the loader could feed 10 or more rounds per minute to the gun. This was a heavy workload, especially in hot weather within the cramped confines of the turret. The ammunition capacity was 97 rounds, a quantity that could be expended in a single major engagement depending on the intensity of the battle. To the right of the gun sat the gunner. He had a periscopic sight mechanically linked to the gun. Wherever the sight pointed, the gun was aimed. This eliminated the need to manually align the sight and the barrel each time. The gun was equipped with a stabilization system in the vertical plane. This meant that when the tank moved over uneven ground, the barrel automatically maintained its set elevation angle, as the mechanism compensated for the pitching of the hull. The gunner traversed the turret horizontally by turning a hand wheel that engaged the electric drive, which was also controlled by a foot pedal. The same pedal activated the electrical trigger for the gun. Vertical stabilization allowed for aimed fire on the move, representing a serious advantage in situations where stopping to fire meant becoming a stationary target. Behind and above the gunner sat the commander. The commander was the key figure in the turret. His task was to observe the entire battlefield, make decisions, assign targets to the gunner, and maintain communication with other vehicles and command. For this, he had his own rotating periscope with all-around vision and a separate hatch in the turret roof. Communication was provided by a two-way radio set, which allowed simultaneous reception and transmission, which was vital in a fast-moving engagement. Inside the vehicle, all 5 crew members were connected by an intercom system utilizing throat microphones, laryngophones, which transmitted voice through throat vibrations rather than an open microphone. This allowed communication even amid intense engine noise. Every crew member had a periscope for external observation. This meant that at any moment, any of the 5 men could observe the situation outside without opening hatches and exposing themselves. The seats in the turret offered a wide range of adjustment, 30 centimeters in height and 12 centimeters forward and backward. For military equipment of that era, this was an unusual focus on comfort. However, there was practical logic behind it. A tired or cramped crew member works slower and makes more mistakes. 2 fire extinguishers inside the vehicle, an escape hatch under the driver's seat, backup manual turret controls, and redundant vision devices. Each of these design choices, small and unobtrusive, pointed to one thing. The designers thought not only about how the machine would fight, but also about how the people inside would survive. This was also part of what made the Sherman a Sherman. The gun is the reason a tank exists. Everything else, armor, engine, suspension, serves one purpose: to deliver the gun to the right place and give it the opportunity to fire accurately and on time. Therefore, the Sherman's armament deserves a detailed and careful discussion. Let us begin with the main gun. On the first production M4 modifications were fitted with a 75mm gun. This gun was inherited from the M3, the intermediate tank discussed earlier. But while the gun on the M3 was enclosed in a sponson with a limited traverse arc, on the Sherman it was placed in a fully rotating turret. The gun was mounted in a mantlet, an armored mount that protected the breech of the gun and provided vertical elevation. The initial version of the mantlet was designated M34. Mounted alongside the gun in the mantlet was a coaxial Browning 7.62mm machine gun, used for engaging infantry at close range when the main gun was unnecessary. The M34 mantlet had a design flaw that became apparent during operation. The gun was held in the mount by trunnions, the metal pivots on which the barrel pitched during vertical aiming. Attached to these trunnions were lifting loops used during gun transport and assembly. In combat conditions, these loops remained in place and created a problem. If they suffered minor damage or deformation, they began to interfere with the free movement of the gun, adding resistance where there should be none. The solution was simple. On the modified M34A1 mantlet, the loops were moved to a different location, and the problem was resolved. However, the fact that this detail required refinement on production vehicles is a characteristic example of how real-world operation reveals issues that are not visible on a test range. Now let us look at what made the Sherman's armament system truly advanced for its time. Gun stabilization. On the Sherman, the gun was stabilized in the vertical plane. The stabilization mechanism worked as follows. A gyroscopic sensor detected the angular pitch of the tank's hull when moving over uneven ground and sent a signal to an electromechanical drive that compensated for these oscillations, holding the barrel at the designated elevation angle. Put simply, while the tank drove over bumpy terrain and the hull pitched, the gun barrel remained pointed where the gunner had aimed it. This made it possible to fire aimed shots on the move without stopping and without presenting a stationary target while firing. In 1942, this was a rarity. Most tanks of that era had to stop to make an accurate shot, becoming easy targets in the process. The Sherman was largely freed from this necessity. To be fair, the stabilization on the early series did not work perfectly. Firing accuracy on the move was significantly lower than from a stationary position. Crews often preferred to stop to guarantee a hit. However, the ability to fire on the move, even with lower accuracy, provided a tactical advantage in situations where stopping was extremely dangerous. Let us move on to the gunner's aiming systems. The gunner's periscopic sight was mechanically linked to the gun. A special linkage connected the sight and the barrel so that when the elevation angle changed, the reticle automatically adjusted. This saved the gunner from having to manually realign the sight and the barrel each time. Horizontal traverse of the gun was performed by the gunner turning a hand wheel, which engaged the electric drive of the turret. Manual controls were used for fine adjustments. A foot pedal on the floor activated both the turret drive and the electrical trigger of the gun, reducing the time between when the gunner acquired the target and the moment of the shot. For protection against infantry and aerial targets, a heavy Browning M212.7mm machine gun was mounted on the turret roof. This weapon, on an open pintle mount, was operated by the tank commander. The heavy machine gun was effective against lightly armored targets, soft-skinned vehicles, and low-flying aircraft, a threat that could not be ignored in active combat zones. The ammunition capacity for the main gun was 97 rounds. The shells were placed in stowage bins throughout the fighting compartment, partially in sponson bins, and partially below the turret floor in wet stowage. Wet stowage bins were metal containers filled with water mixed with anti-corrosive additives surrounding the ammunition. If the ammunition bin was penetrated, the water absorbed some of the energy and reduced the risk of immediate fire. This solution was not implemented immediately. Early series Shermans carried their ammunition in dry stowage bins. Combat experience showed that if the armor was penetrated and the ammunition bin was hit, the vehicle caught fire very rapidly. Crews gave the Sherman a nickname that stuck and entered historical literature, but that is a complex and difficult topic we will return to. Wet stowage became one of the answers to this problem. It was not a complete solution, but it was a significant step forward. By 1944, it became obvious that the 75mm gun was struggling to cope with the thickened armor of the enemy's newer vehicles. The response was the installation of a 76mm gun with a longer barrel and a significantly higher muzzle velocity on a portion of the Shermans. This modification substantially improved the vehicle's anti-tank capabilities. The British went even further. They mounted their own weapon, the 17-pounder 76.2mm gun, which offered very high armor penetration on the Sherman chassis. This version, named the Sherman Firefly, became one of the few Allied vehicles capable of reliably engaging heavily protected enemy armor at realistic combat ranges. But there was still time before these modifications, before Normandy, and before 1944. First, the Sherman had to pass its first real test, and that test was North Africa. September 1942, Port of Alexandria, Egypt. Transport ships were being unloaded in a hurry. On the pier, vehicles painted in desert sand colors were lined up. British technicians walked around them with documentation, checking serial numbers and verifying completeness. 300 Shermans, the first major batch. The British Eighth Army was in a difficult position at the time. After a series of setbacks in Libya and a retreat to the Egyptian border, the front line had stabilized near a small railway station called El Alamein. The German Africa Corps, commanded by Field Marshal Erwin Rommel, was pressing the British positions, and supplies for both sides were stretched to the limit. However, the initiative remained with the adversary. The Shermans arrived at the right moment. British tankers familiarized themselves with the new machines quickly, as there was no time for lengthy training. Technicians from the American support groups held briefings right by the vehicles, explaining the design through interpreters. The crews made short test drives, getting used to the steering, visibility, and handling characteristics. The first thing everyone noted without exception was the drivability. Compared to British tanks of that period, the Sherman was predictable and responsive. It had a 5-speed gearbox with clean shifting, smooth differential steering without jerks, and a suspension that kept the vehicle stable even on the stony ground of the African desert. The second aspect was visibility. Periscopes for every crew member, a rotating turret floor, and a comfortable position for the commander with his own hatch all provided the crew with a picture of the battle that was unavailable in many other vehicles of the time. The third was the gun. The Sherman's 75mm gun could penetrate the armor of the main German medium tanks of that period at ranges up to 1,000 meters. The German Panzer IV with reinforced armor could be penetrated, as could the self-propelled guns based on it. This represented a parity that British tankers in Africa had not enjoyed for a long time. On October 23, 1942, the Second Battle of El Alamein began. The Eighth Army, under the command of General Bernard Montgomery, attacked the positions of the Africa Corps. Within the British armored divisions, the Shermans operated not as a novelty, but as the main striking force. The battle lasted several weeks. Conditions were harsh, with daytime heat reaching 40 degrees Celsius, nighttime cold, and sand that found its way into every crevice. Engines ran at their limits due to the dust load, and repair crews got very little sleep. Under these conditions, the Sherman demonstrated the quality for which it was highly valued: reliability. The air-cooled Continental R975 engine handled the desert environment better than many liquid-cooled engines, which suffered from overheating and coolant leaks. The suspension held up, the transmission functioned, and while vehicles did break down, as any machinery does under real combat conditions, they were repaired quickly. By November 1942, the Africa Corps began its retreat. El Alamein became the turning point in the North African campaign. The Sherman played its part in this success, but an honest discussion requires honest assessments. From the very first battles, crews encountered an issue about which thousands of pages would subsequently be written. When the Sherman's armor was penetrated, especially on the sides or rear, the vehicle caught fire quickly. The hydraulic fluid of the turret traverse system ignited at high temperatures, and dry ammunition stowages detonated. Crews who managed to exit the vehicle through the hatches or the escape hatch under the driver survived, while those who did not, did not. British tankers gave the Sherman a nickname, Tommy Cooker, after the portable stove British soldiers used in the field to cook food. The implication was direct and unsparing. The Americans were aware of this problem, and it was one of the primary reasons for the introduction of wet ammunition stowages on later production runs. But in 1942, that solution was still under development, and the crews had to work with what they had. It is important not to go to extremes here. The flammability of the Sherman was a real problem, but it was not unique. Most tanks of that era risked catching fire when their armor was penetrated and the ammunition was hit. German, Soviet, and British vehicles all shared this risk to some degree. The difference lay in how quickly it occurred and how much time the crew had to escape. The Sherman was not the best in this regard, but it was not an exception either. Another problem identified in Africa was insufficient mobility on soft terrain. The standard track, about 16.5 inches wide, resulted in relatively high ground pressure for a 30-ton vehicle. In the sandy desert, this meant the Sherman would sometimes sink where lighter or wider tracked vehicles passed without difficulty. This would also be addressed later. Meanwhile, in November 1942, the Africa Corps was in retreat, and the Sherman had proven that it could fight. The next lesson awaited it in Europe, and there, the rules were entirely different. A good tank is not one that turns out perfect on the first attempt. Perfect tanks do not exist. A good tank is one that is capable of changing, that absorbs combat experience, and responds to it with concrete technical solutions. By this standard, the history of the Sherman's upgrades is one of the most indicative examples in the history of 20th century armored vehicles. Let us start with the most obvious aspect, the tracks. The African campaign showed that the standard track, at about 16.5 inches wide, was too narrow for soft ground. However, it became a major problem not in the desert, but in Europe during the autumn and winter of 1944, when the fields of Normandy and Belgium turned into a sea of mud. The 30-ton vehicle on narrow tracks bogged down, got stuck, and lost mobility exactly when mobility was needed most. The answer was the horizontal volute spring suspension, designated in technical documents as VVSS. This new running gear used wider road wheels and, crucially, a track about 23 inches wide, nearly 7 inches wider than the standard one. This reduced ground pressure and allowed the vehicle to move confidently where its predecessor would have bogged down. Externally, tanks with the new suspension are easy to distinguish from early vehicles by their wider tracks, modified bogie shapes, and a different lower hull silhouette. The modification with the horizontal suspension received the designation M4A3E8. American tankers nicknamed it the Easy 8 from the pronunciation of the letter E and the number 8. It earned a reputation among crews as a reliable and mobile vehicle. Now, regarding the engines, and here the story becomes interesting. The Sherman never had a single standard engine. This seems unusual, but there was a clear logic behind it. When production expanded across several large factories in 1942, it became clear that there were not enough Continental R975 aircraft engines to go around. The aviation industry had priority, as aircraft needed engines no less than tanks. Consequently, they made a decision that in other circumstances might have seemed ill-advised. Different factories would install different engines in the Sherman. The Chrysler plant in Detroit developed its own solution, the A57 multibank engine, which consisted of 5 Chrysler automobile engines arranged around a common crankcase with a single output shaft. It had 21 cylinders. The power was about 470 horsepower. The design was so complex that mechanics initially looked at it with open dismay, yet it worked. Other plants used the Ford GAA engine, an 8-cylinder liquid-cooled engine producing about 500 horsepower, which was developed from an aircraft engine design. Still others used the General Motors 6046 diesel, a twin unit consisting of 2 6-cylinder diesel engines. The diesel versions of the Sherman, designated M4A2, were supplied in significant numbers under Lend-Lease to Soviet forces. Soviet drivers and mechanics spoke highly of them, noting that the diesel engine was less prone to catching fire than gasoline ones, and its fuel consumption was lower for comparable power. This variety of engines created a logistical headache, as spare parts for one type of engine did not fit another. However, it also ensured that production did not stop for a single day due to a shortage of any one component. Industrial flexibility as a strategy. Now, the gun. This is a fundamental point. By mid-1943, it was obvious that the enemy was actively fielding new vehicles with reinforced armor. The German Panther tank had 80 mm of frontal armor at a sloped angle, while the Tiger had 100 mm of vertical frontal armor. The Sherman's 75mm gun, with a muzzle velocity of about 600 meters per second, struggled against these targets. At realistic combat ranges of 500 to 1,000 meters, it could not penetrate the front armor of the Panther at all. The response was a 76mm gun with a barrel length of 52 calibers. With a significantly longer barrel, the projectile had more time to accelerate, increasing the muzzle velocity to about 800 meters per second. This substantially improved armor penetration. Shermans with the 76mm gun began arriving in units in 1944. However, a problem arose that is sometimes overlooked. The American command hesitated to introduce the new gun longer than the situation demanded. Some officers believed the 75mm gun was sufficient for the tasks at hand, and they were correct in the sense that the majority of combat engagements did not involve heavy armor, but rather infantry, fortifications, and lighter targets. For those tasks, the 75mm was adequate. But in direct encounters with heavy German tanks, the difference proved critical. The British found their own solution to this problem earlier and more radically. They took the Sherman chassis and installed their own weapon, the 17-pounder gun. This gun had a caliber of 76.2 millimeters, but with a much longer barrel and a significantly higher muzzle velocity, about 950 meters per second when using discarding sabot ammunition. The resulting vehicle was called the Sherman Firefly. The Firefly could penetrate a Panther from the front at ranges up to 1,000 meters, and under certain conditions, a Tiger as well. This made it one of the most effective anti-tank vehicles in the Allied inventory in 1944. German tankers were aware of this. Evidence suggests that in combat, they first tried to identify which Shermans in front of them were standard models and which were Fireflies, concentrating their fire on the latter. Alongside the gun and running gear, work on armor protection continued. On several late modifications, the frontal armor was reinforced, the angles of the plates were changed, and better protection was achieved in the frontal aspect. Some crews independently welded additional armor plates, spare track links, or sandbags onto their vehicles, anything that might provide an extra chance of survival. This was not part of the official design, but it was a real-time reaction of the men to the conditions in which they fought. By the end of production in 1945, a late-series Sherman and a 1942 model Sherman were similar only in their general outline. They shared the same basic layout and name, but had different suspensions, different guns, different engines, reinforced armor, wet ammunition stowage, and improved sights. A vehicle that began as a temporary response to a specific request in 1941 had evolved over 4 years into an entire family of variants. And this family had not yet finished fighting. May 8, 1945, Europe. The guns fell silent. Columns of vehicles stood on the roadsides. Crews climbed out of their machines and looked at the sky, simply because they could. Among these vehicles were Shermans, many Shermans. They had traveled from the Normandy beaches to the banks of the Elbe, from North Africa to Rome, and from the Pacific Islands to Manchuria, where Soviet forces used Lend-Lease Shermans in the August 1945 campaign against Japanese troops. The vehicle fought on all major theaters of that war simultaneously, in different armies and in diverse climatic conditions. This in itself was unique. But the Sherman story did not end in May 1945. It continued immediately. June 1950, the Korean Peninsula. North Korean forces crossed the border at the 38th parallel and advanced rapidly southward. Their armored units employed Soviet T-34 tanks, vehicles that American forces had not encountered in Europe but knew enough about. The first American units deployed to Korea had M24 Chaffee light tanks, which were virtually defenseless against the T-34 due to the significant disparity in armor and armament. The situation changed when Shermans began arriving in Korea, primarily the M4A3E8 modification with the 76mm gun and wide tracks. The result was unexpected for those who had considered the Sherman obsolete. The EZ-8's 76mm gun reliably penetrated the armor of the T-34 at realistic combat ranges. The vehicle's mobility on the hilly Korean terrain, with its narrow roads and rice paddies, proved sufficient. The reliability refined over years of production and operation remained intact. The Sherman fought in Korea until the armistice in July 1953. This represented 11 years of active service, from the first battles in Africa in 1942 to the final shots on the Korean Peninsula. But even that was not the end. After the end of the Second World War, the United States transferred a significant number of Shermans to allied and friendly nations. The vehicle served in the armies of France, Israel, Egypt, Syria, Jordan, Mexico, Argentina, Brazil, Chile, Pakistan, India, and dozens of other states. Israel deserves special mention. Israeli armored forces obtained Shermans in the late 1940s and treated them not as obsolete equipment, but as a platform for deep modernization. Israeli engineers mounted a French high-velocity 75mm gun on the Sherman chassis, and later a 105mm gun. They reinforced the armor and replaced the engine with a diesel unit. The resulting vehicle, named the Sherman, fought in Israeli armored units in 1956, 1967, and even 1973. 31 years after its adoption into service, the vehicle was still in the field. This was not just longevity, it was a testament to the development potential built into the design, a margin that the designers of 1941 might not have fully realized themselves. Now, regarding the Sherman's place in history, here we must be objective. Debates about the Sherman have not subsided since the end of the Second World War. Some historians call it underprotected and undergunned for the European theater of 1944 to 1945. Others point out that the mass production, reliability, and ease of repair of the Sherman provided the Allies with the armored superiority that ultimately decided the outcome of the campaign. Both sides are correct in their respective arguments. The Sherman was not the best tank of the Second World War in a narrow technical sense. In terms of its ratio of armor and armament to vehicle weight, that is a fair assessment. However, it was an effective system when viewed more broadly, taking into account production, logistics, maintenance, adaptation, and scale of use. 49,234 vehicles, 8 major operating nations during the Second World War, more than 10 years of active service, participation in all key campaigns from 1942 to 1953. No other Allied tank has such a record. There is another point rarely mentioned in discussions of military hardware. The Sherman was one of the first mass-produced tanks in which the designers deliberately focused on crew survivability. The escape hatch under the driver's seat, the rotating turret floor that reduced the risk of injury during traverse, the wet ammunition stowages on later series, redundant control systems, and fire extinguishers inside the vehicle. These were not random details, they represented a fundamental approach. The German design school of that period prioritized firepower and armor protection. The American school, in addition to these factors, considered what happened to the people inside when things went wrong. This difference in philosophy is as important a part of the Sherman's history as armor thickness and gun calibers. Today, the M4 Sherman can be seen in museums on all continents, in Aberdeen and Bovington, in Kubinka and Saumur, and at memorials in Normandy, where some vehicles still stand on the very fields where they fought. They are also found in private collections, where enthusiasts restore them to running condition and drive them in parades. Each of these vehicles is not merely an exhibit, it is physical evidence of decisions made by engineers in 1941 in the quiet offices of the Aberdeen Proving Ground, decisions that ultimately materialized in nearly 50,000 machines and the lives of the men who served in them. There is a question that anyone studying the history of the Sherman asks sooner or later. Could they have done better, given the same deadlines, the same industrial potential, and the same constraints of 1941? Everyone has their own answer to this question. But the fact remains, what was accomplished changed the course of events, and a vehicle conceived as a temporary solution to an urgent request became one of the symbols of an entire era. The M4 Sherman, 49,000 vehicles, 11 years of service, and a name remembered to this day.